Let me do it again. So I'm happy to have Anna Romanov from University of New South Wales, Australia. She's going to talk about Lusztig-Vogan categories and a categorical approach to real reductive groups.
Great. Thank you very much. Thank you for having me. It's really nice to be here. This is my first time in Korea, so that's been a lot of fun. So what I want to tell you about today is a bit of a merging of my childhood and my adolescence in some sense. So I did my PhD in the United States at the University of Utah, and my supervisor was Dragan Milicic, but I also worked closely with Peter Trappa. And if you know these people at all, they're in the world of real reductive groups and unitary representations. And Dragan specifically studies these using bimodules and geometric representation theory. So this is kind of my childhood. I was brought up in this world of classical geometric representation theory. And then when I finished my PhD, I moved to Australia, and I went to the University of Sydney for a postdoc. And at University of Sydney, there are many geometric representation theorists, but they use a completely different set of tools. So Sydney's really known for categorification and diagrammatics and these types of tools. And they think about problems that are really similar to the problems of my youth. So problems about representation theory of Lie groups or Lie algebras, but they do so using these categorical tools. And so when I came to Sydney, I learned all these tools and I wanted to try to meld my two worlds. And the result is this research program that's been going on for a while now in different capacities. And this is kind of what's come out of it. So what I've tried to do here is look at questions about classical representation theory of real reductive groups using tools in categorification. So I'll tell you in much more detail what all of this is. I should also say that I'm very unfamiliar with my audience today. I'm not really sure what world you guys come from and what you study. And so I'm very happy for questions. So I'm very happy for you to stop me at any time and ask questions. I love questions. I'm not at all attached to getting to the end of my talk. Also, I was just told I have up to 90 minutes and I only planned 50 minutes. And so there's plenty of time. So I would just like to tell you a nice story today, but I can only tell you a nice story if I know where you are. So feel free to stop me if you need to. Okay, so here's my plan. I guess I should point it this direction. Oh, come on. Are you not working? Oh, now everything's frozen. Let's see. Is that working? There we go. Okay, here's my plan. So I want to start by telling a very classical story of B orbits on G mod B. Here, G mod B is a flag variety associated to a reductive algebraic group, complex reductive algebraic group. B is a Borel subgroup. This is the geometry of representations of complex semisimple Lie algebras. So I'll start by telling this classical story. And then next, I want to change the story a little bit to the world of K orbits on G mod B. This is also a geometric world, but this is a geometric world which captures the representation theory of a real reductive Lie group. And both these first two sections are going to be somewhat motivational. So I'm not going to tell you a lot of exactly the details of what I'm saying. I just want to get some ideas across. The story might be very familiar to you. It might not. If it's not familiar to you, once I get to section 3, I'll be precise. So in section 3, I'll introduce some categories. And these are categories whose objects are bimodules over some polynomial ring. And these categories capture information about real reductive groups. And I'll define them precisely. And then finally, I want to give you many examples. We run a seminar in Sydney, which is kind of joint between UNSW and University of Sydney. And it has some rules, or the rules are maybe axioms of the seminar. And the most important one is examples, examples, examples. So I try to make sure all my talks follow the rule of the informal Friday seminar and have plenty of examples. So that's what I'll get to at the end. So let's start with a nice story. So here's a story that's well loved to categorical representation theorists. Oh, you can't see the very top of this, but the top thing says that G is a complex semisimple algebraic group, like SL2C, 2 by 2 complex matrices of determinant 1. And if we have such a group, we can build this geometric setup. We can look at a certain variety associated to the group, the flag variety, which has different incarnations, one of which is to take the group itself and take a quotient by a certain subgroup, a Borel subgroup. In SL2, this is the subgroup of upper triangular matrices. This has a natural structure of a variety. This variety has a natural action of the group and any subgroup. So in particular, we can take the action of a Borel subgroup, so upper triangular matrices, on this variety, which we realize is a quotient. And this geometric setting is what I call the geometry of categorial. So this captures information about representations of a complex semisimple Lie algebra. Categorial is a certain class of representations that includes finite dimensional representations, highest weight representations, and Verma modules. Now, this geometry is especially nice because it has a closely related combinatorics. So if we look at these orbits, this collection of orbits, this stratifies the variety, and each of the strata can be parameterized by an element in a finite group, the Weil group. And this is called the Bruhat stratification. And it turns out that a lot of information about this geometry can be reformulated in terms of information about this finite group. So for example, each of these orbits is an affine space of a different dimension. And the dimension of that affine space is captured within something about the group element. So something called the length of the group element corresponding to that orbit tells you its dimension. And then if we want to know about closure relations between these orbits, they're all different dimensions, and some of them are contained in the closure of other ones. These closure relations are also captured in the group information via a certain partial order that you can define on the group. So this geometry reformulates in terms of a certain combinatorics, in terms of the Weil group. But if we are geometers, well, we could just go from here and study this landscape combinatorially. But if we're geometers, we might want to keep going. And if we have some situation where we have groups acting on a variety, it's very natural to sheafify this and look at sheaves on the variety that are equivariant with respect to that group action. And so in this situation, it turns out that it's a bit better to work within the derived category instead. But we can sheafify this picture and get to this gadget called the equivariant derived category, whose objects are roughly complexes of equivariant sheaves with respect to this group action, constructible sheaves. So this is a big geometric machine that now carries all the information about this geometry. But there's a natural functor from this equivariant derived category to a more algebraic landscape. And this functor is the hypercohomology functor. So if we have a complex of sheaves, we can just take Homs against the constant sheaf, which we consider as a complex concentrated in degree 0. And this gives us a natural map from our geometric world to a sort of algebraic skeleton. And what we land in is a category of graded modules over the equivariant cohomology ring of the flag variety with respect to this Borel action. Okay, so this is a relationship between something geometric and something algebraic. But does the functor actually capture information? It turns out that if we restrict to a certain very natural subcategory living within the equivariant derived category, this functor is fully faithful. So it captures all the information about this subcategory. And this subcategory is very simple. So I've written it as HSS to stand for the semi-simple category, because its objects are, so within the equivariant derived category, we have these certain IC sheaves. And the objects in the semi-simple Hecke category are just direct sums of shifts of IC sheaves. So we build a category quite naively. We just take these certain objects in our category and take all direct sums and all shifts and take that category. This thing I'll refer to as the geometric Hecke category because it categorifies the Hecke algebra. So this is one of the many categorifications of the Hecke algebra, is this complex of semi-simple sheaves in the equivariant derived category. And for our purposes, it's exactly the piece where this hypercohomology functor is fully faithful. So that means that we can work entirely within this algebraic world, which is a reasonable algebraic world. So if we want to, so we landed in the category of graded modules over some ring, which is only useful if the ring is reasonable, but in this case, the ring is quite reasonable. So if we compute the equivariant cohomology of G mod B, this is just the tensor product of a polynomial ring with itself. What the polynomial ring is has something to do with the data of the group that we started with, but for our purposes, it doesn't really matter. It's just a polynomial ring in some number of variables. And we've realized our kind of complicated geometry as embedded within this category of modules over this tensor product of polynomials. So if we want to go even farther, we just need to find the essential image of this functor to get an equivalence of categories. So one way to think about this, I sort of said this out loud, but is that this here is an algebraic skeleton of what's going on in this complicated geometric world. So we started with some natural geometry, sheafified, and then captured its algebraic skeleton. And we can go one step further. So if we have modules over a tensor product like this, we can just think about them as bimodules instead, where the first tensor factor acts on the left and the second one acts on the right. So we can take all of these modules and think about them as graded bimodules. And then
Here, RW is the invariance.
yes, exactly. So the RW here is this W, the Weyl group, which is capturing information about the orbits, shows up in this picture as well. It naturally acts on this polynomial ring, and we're taking the tensor product over these invariants. But this category naturally embeds into the category of RR bimodules, where we forget the RW. And this is a fully faithful functor here, so we don't lose any information by thinking about these modules over this ring as RR bimodules instead. Okay, so I said that, so this is fully faithful, which means that we can think about the geometric category, Hecke category, as sort of embedded inside this world. And what's its essential image? Its essential image is exactly the category of Soergel bimodules. So I won't tell you precisely what Soergel bimodules are, other than that they are the essential image of this functor, but they can be described algebraically very specifically. So there's the objects in this category are bimodules over a polynomial ring, and they're subject to certain conditions. We can carve out the ones that appear as the essential image. Okay, so we've kind of moved along our geometry and ended up in some world that's quite algebraic. We have a category of modules. And it turns out that we can go, because this is fully faithful and this is its essential image, all of these arrows to here are an equivalence of categories. So this category also categorifies the Hecke algebra. And I'll call it the algebraic Hecke category for that reason. And it has a diagrammatic version. So there's a certain category we can define whose objects are just strings of elements in this group here, and its morphisms are defined via string diagrams. And this category, there's an equivalence between this diagrammatic version and Soergel bimodules as well, due to Elias Williamson and Romanov. And the whole point of this is this whole machine was built by various people at various times as a machine to study the representations of a complex semisimple Lie algebra. So how does it actually work? If you're not familiar with the story, the way that it worked is that this category was first defined by Soergel. He called them special bimodules, of course, and not Soergel bimodules. And he defined this category because he was trying to prove the Lusztig-Vogan conjectures, which are a statement about multiplicities of irreducible highest weight modules and Fermat modules. And he kind of built all of this chain in order to try to derive an algebraic proof of this statement. Because there's a direct way that you can relate objects in this category back to representation theory, which I won't talk about today. He didn't quite succeed in his program because it was missing a little bit of extra information. And so the extra was given by Elias Williamson when they gave this diagrammatic version of the Hecke category. And they completed Soergel's program to prove the Lusztig-Vogan conjectures using this arrow and the rest of them. So this whole machine told us really nice information about semisimple Lie algebras in a classical way. And since then, it's appeared all over the place. So one really nice feature of Soergel's program is that up here, when we're in the world of geometry, our Weyl group is always finite. This is the Weyl group associated to semisimple Lie algebra, or the semisimple Lie group that we started with. But down here, these categories, their input data can be that Weyl group, but they also make sense if we define them for any Coxeter group, one that might not necessarily be associated to semisimple Lie algebra. So these categories are more general, and then the more general versions of these things ended up being useful across representation theory in other settings as well. I'll pause here and ask for questions. Because again, I should say, I have no idea if I'm telling you something that you're very, very familiar with, or if you've never heard this story before. So are there any questions on this slide?
What's a good source to learn what you just said in this slide?
So a good source to learn this bit is there's a really lovely textbook called An Introduction to Soergel bimodules, which came out of an MSRI summer school about 10 years ago now. And that describes Soergel bimodules and their diagrammatics very well, but it doesn't describe the geometry. So this arrow, probably the best place to understand it or to find the best resources are various papers by Jordi. I think he had a really lovely ICM report from like the last ICM. So, and that describes something related. It describes parity sheaves, but it describes this geometry, how it works in both the positive case and the characteristic 0 case, which is what I'm describing here. So that's probably the best resource for this arrow. And then for this world, this should be contained in any classical textbook on reductive algebraic groups. So something like Springer is where I learned this from, Springer algebraic groups, but there are other settings as well.
And this slide is about 0 characteristic.
Yes, exactly. Everything here is over C. So I'm talking about a complex algebraic group, and yeah, everything in sight is complex. Thank you for the question. So like I said before, I've given you a whole bunch of things and not defined them. I will define stuff precisely in a bit, but this is meant to be motivation for where my story starts and what I want to continue.
Here, diagrammatic category can be defined for arbitrary constituents.
Yes, exactly. So this category and circle bimodules as well can be defined for arbitrary Coxeter group.
So somewhere the diagram cannot be extended. Right? So,
exactly. So geometry doesn't exist unless we have a Weil group. So all of this top part only makes sense if W is a Weil group, but all of this bottom part makes sense for an arbitrary Coxeter group. Yeah, Valentine?
Can you define Soergel bimodules or the diagrammatic category for something like an extended affine Weil group?
Yep, because it's a Coxeter group, isn't it?
No, so I mean, what I mean by extended is not the Coxeter group, but when you have to add some like length 0 element.
So like corresponding to a like an affine Lie algebra or something. Those guys. I think so.
Okay.
I'm not an expert in that, but I think that you can.
Okay.
Yeah.
But everything works for any Coxeter group.
Yeah. All of the algebraic bit works for an arbitrary Coxeter group. In particular, they can be infinite, and so there are a lot of Coxeter groups that are not Weil groups. So this is an enormous extension to extend this to arbitrary Coxeter groups, and they show up in all sorts of other ways. I was just in a talk a couple of weeks ago about how a certain hyperbolic Coxeter group is related to certain polytopes, which one can describe using algebraic geometry. And yeah, they show up in all sorts of interesting places. Okay, so this is a somewhat classical story. This was done, when was Soergel doing this? This is maybe like the 90s, maybe late 80s. And then this is the 2014, I think is when this result came out. So this is a well-loved story at this stage in categorical representation theory. But here's another, so the upshot of this is meant to be that the geometry of categorial is given by B orbits on G mod B, which we can reformulate algebraically or diagrammatically using Soergel bimodules. So here's another very classical setting in representation theory. That's the setting of real groups. So for me, what is a real group? If we start again with a complex semisimple algebraic group, then we can look at a holomorphic involution on this. So some holomorphic function that squares to the identity. And this allows us to take a subgroup of this group by looking at fixed points under this involution. And to me, these three things are the data of a real group. Now I'll pause for a second and explain why. Again, you can't see the top, but it says.
You can try
Can I get that?
pressing OK.
Oh, this, okay. It's two okay. Okay.
Yeah.
Oh, perfect. Okay. There we go. Now we can see it. So why does this determine a real group? Well, I've lost my again. So if we start with a complex Lie group, I'll have a running example down here below. You're welcome to think in terms of this example for the rest of the talk if you like SL2C. Well, this thing has the structure of a complex manifold, so it makes sense to talk about holomorphic or anti-holomorphic involutions. If we take an anti-holomorphic involution on our complex group, this is just an involution that's holomorphic in the conjugate. And for example, a classic anti-holomorphic involution is if we take a matrix in SL2C and we conjugate every entry of the matrix, that's anti-holomorphic. And if we look at the fixed points under an anti-holomorphic involution, we actually get on the nose a real Lie group. So for example, if we look at matrices who are fixed under this involution, that just means their entries are equal to their conjugate, which exactly means their entries are real. So the fixed points are SL2R living inside of SL2C. So here's a real Lie group. I'm claiming that my data is somehow capturing information about real Lie groups. And how does it do that? Well, we could also look at holomorphic involutions instead. So if I take a holomorphic involution, for example, here's one on SL2C, I can take a matrix, I can take its transpose inverse. That's a holomorphic involution. And if I look at the fixed points under that, I end up with a complex Lie group living inside of my initial complex Lie group. So in this example, if I take matrices that are fixed under this, those are exactly matrices whose transpose is equal to their inverse. And so this is just SO2C, the complex orthogonal group. And this is a complex group. And the key here is that anti-holomorphic involutions and holomorphic involutions are in bijection up to conjugacy. And the way that bijection works is if we have a holomorphic involution, there's always a unique holomorphic involution whose fixed points are compact. And we call this the compact form of a group. This is related to the fact that every Lie group or all compact subgroups of a Lie group are conjugate to each other, has a unique compact subgroup up to conjugacy. And so if we compose two anti-holomorphic involutions, we get a holomorphic involution. So if we compose our anti-holomorphic involution with the unique compact one, that uniquely determines for us a holomorphic one called the Cartan form of our involution. So these two sets are in bijection. And then the beautiful part of this story is that if we complete this diagram, it commutes in some sense. So if we first apply our anti-holomorphic involution, take the fixed points, and then we apply our holomorphic involution, take the fixed points, we end up with the maximal compact subgroup of our real Lie group here. And then if we first do the holomorphic one, take the fixed points, then take the anti-holomorphic one, take the fixed points, we end up at the same place. So here, if we take the fixed points of SL2R under the involution that takes transpose inverse, we end up with SO2, the real group. And down here, I think you can't quite see my highlighting, but this world here is a world that's legitimately the world of real Lie groups. So this is a real Lie group and its maximal compact subgroup. This is a world that's well suited for analysis. And so classical study of real Lie groups used analytic techniques to try to understand the representation theory of a real Lie group in terms of representations of its maximal compact subgroup plus some other information. But up here in the upper bit of the diagram, we now have two complex Lie groups, or actually complex algebraic groups if we like. And this is a world that's well suited for algebraic geometry because we have some subgroup of a complex group. And then the beautiful insight of Harishchandra and many others is that it doesn't matter which world we work in. So there are explicit bridges that let us study representations of real Lie groups by instead studying representations of G that restrict in a certain way to K. And we can translate this information exactly back to information about a representation of a real Lie group. So people study representations of real Lie groups in different ways. Functional analysts study them downstairs in this world. I learned them upstairs in this world because this is the world where geometric representation theory applies. So for me, I forget about the Lie group itself, and to me, a real group is exactly this data. So back to my previous slide, that's why I say that this is a real group, because through some complicated procedure that I never actually do, we can take all the information we gain, translate it back to information about representations of real groups. Okay, so this is quite a classical setting. This setting is even older than the previous one, really. I mean, people have been studying representations of real Lie groups since like the 1930s, and studying their unitary representations in particular has been a problem for a long time, and many mathematicians have dedicated lifetimes to it. And there are many tools that have been built. And so one of them is this geometry. So one can study representations of a real group by looking at K orbits on G mod B. And now K here, both K and G are complex. But this feels awfully similar to the previous slide. So a very natural question is, we have some geometry which captures information about representation theory of real groups. Can we play the same game that we played before? So we can certainly try. So here's our geometry of real groups. What was my first step? Well, I looked at the K orbits on G mod B. And in the previous slide, this had a really lovely combinatorial description in terms of the Weil group. And in this setting, there's kind of combinatorics, but everything is already a bit more complicated. So one can write down relationships between these orbits using not just a finite group, but some more complicated gadgets called clans and other things. Many people have worked hard to describe this combinatorics, but it tends to be type specific. So there's combinatorics that works for type A or type C, but there isn't really a unified theory like there is of Weil groups. And one reason why this is harder is that in the previous example, each of the orbits was just affine. It was an affine space. And so in some sense, the relationship between the orbits was somewhat simple, so we could capture it just within a group. But here, our orbits are not necessarily simply connected, and they can be significantly more complicated. And so one would expect that anything describing their combinatorics needs to be a bit more evolved. But for the purposes of geometry, that doesn't matter. It still makes perfect sense to look at the orbits of this group on this variety and sheafify. And so we can do that. If we sheafify this, we can, instead of thinking about the B equivariant derived category, we can think about the K equivariant derived category. This works just the same as the B equivariant version. It's a nice mathematical object, but there's something going on here, because since our orbits are no longer simply connected, we end up with some interesting non-trivial local systems within this derived category. But we can still try to play the same game. We can cut out the category of semisimple complexes in the equivariant derived category, apply hypercohomology. Again, this is a natural functor. It just homs against a constant sheaf. We end up with a category of modules over some ring. Again, the ring has quite a nice description. So the ring is a tensor product of two polynomial rings, but now they're different polynomial rings. So we have the exact same ring as before on the right, but on the left, we have invariance of that ring under some action of a group related to K. And exactly what this is has to do with those two groups that I started with. So if you remember my little diagram, I had SL2C and SO2C. The Weyl group of SO2C naturally lives within the Weyl group of SL2C, and I look at invariance under the smaller Weyl group here.
Can I ask one
Yeah.
question?
Please.
So there, instead of real decomposition, can you just like using the universal decomposition? Is it helpful? Or?
Oh, no, that's a good idea. It could be helpful. So there are, yeah, that's a great point. So what I've done here is that this decomposition has a direct relationship to admissible representations. And so that's why I'm starting with this as the geometry of real groups. But as you point out, there are many interesting decompositions of real groups in different ways. And one could certainly run this machine with a different one, and I don't know what would happen. It's a good question. So I'll tell you in a second how this plan has a few failures. I'm about to get to one of the failures. And so in the future, I would really like to try to figure out how to change this geometry in such a way that I can kind of patch together and make up for the failures. And so that could be one of the ways. Thank you.
Can I ask a question?
Yeah.
So this is what you refer to as a real group.
Yes.
So you don't really work with like Lie group over reals.
No.
Does this tell you anything about those things if you actually want to try these things for like real groups, like homogeneous space for real Lie groups and
Oh, so like let
left
G
and-
be real?
Yeah.
Yeah, I think people think about this, but I don't really. But you could, I mean, presumably you could do that, but you would end up, everything would be over R. So you'd have sort of categories. So I'm not
Yeah,
sure how
like
these equivariant derived categories.
descriptions and so on, do they exist for the real part?
I think so. There's this really beautiful thing called what is it? It starts with an M. It's like there's a correspondence between this complex picture
Yeah.
and exactly what you're describing, the real picture. I think Matsuki duality or something like that. It's called something like this. And so there is a way that you can describe this entirely in terms of real algebraic geometry. And so I think, no, I remember it now. So the orbits are described. There's like a bijection between each setting where it kind of flips the orbits on their head in a really interesting way. So like the biggest orbit in this picture becomes the smallest orbit in the other picture, but their closure relations and stuff can exactly be captured via this, I think Matsuki duality is what it's called. And you can go, it's like an explicit map that lets you go between them. So you can think in terms of that world. I don't know it especially well, but yes, this is a world people think about. What I'm not sure about is if it messes with this equivariant derived category machine.
Yeah, that's okay.
Yeah. But yeah, that's true. And yeah.
Another question. So in this derived category, are you taking some T structure and part of it?
No.
No?
So I'm doing something much more naive. So I'm taking some big triangulated category, and out of it, I'm carving an additive subcategory. So nothing I do is abelian. These are all additive categories. And this additive subcategory is a really simple one. I'm just taking all the IC sheaves, taking the category that only has their direct sums and shifts. And so you could take, like one thing you could do, actually, this is a specific way you can relate this to real groups is if you take the right structure and take the right T structure, you can define perverse sheaves in here as the heart of that T structure. Those K equivariant perverse sheaves, you can them through the Riemann-Hilbert correspondence, you get some K equivariant D modules. You can take the global sections of those D modules, and then you legitimately get GK modules, where G is now a complex Lie group, K is this K. Those GK modules are representations of the real Lie group, like on the nose. That vector space can be given the structure of a representation. And so if you do some other business, you can go straight from this world to the representations. But what I'm doing here is I'm doing something easier. So I'm doing something like a little bit more basic because I'm not trying to build equivalences of categories necessarily. I'm just trying to capture sort of combinatorial information about these categories that tell us about representations. Okay. Thank you all for asking questions. Anyone?
What's the file group of SO2C?
Oh, it's funny. It's quite boring. It's just trivial. So it's not really a great example. We need to get a bit bigger before we get an interesting example. Okay. So I said earlier that my method has flaws. I'm about to tell you the first of those flaws. So if you remember this picture before, this all worked great because this functor was fully faithful. So that let us take this semi-simple piece of the equivariant derived category and think about it entirely within this algebraic setting. But that doesn't work here. This functor is no longer fully faithful. And the problem are these local systems. So the orbits are not simply connected, which allows non-trivial local systems into our setup. And then this hypercohomology functor, it doesn't see non-trivial local systems. So it loses that information. So that's too bad. But we can still do something. So there's a large piece of the semi-simple category on which this functor is fully faithful. And we can describe this piece really explicitly. It's the piece that's generated by closed orbits. At this stage, generation doesn't make any sense because I haven't told you anything about action, so I'll tell you that in a minute. But this is a very natural thing to define within here. And on this piece, hypercohomology is fully faithful. Great. Okay, so with a slight adaptation, we've recovered our picture, and we end up in some category of modules over a tensor product of polynomial rings. Again, we can move to bimodules quite easily. And then if we look at the essential image of this functor, we get something. And that something is what I call a Lusztig-Vogan category. By the way, I should have said this earlier. I'm making some assumptions about my real group here, which are not necessary, but they make the story easier. The assumption is that my real group is equal rank, which means that the G and K share a maximal torus. So I can do this for non-equal rank groups, but all these rings get more complicated and it's not as streamlined, so I will not today. So these are the categories in the title. I've gotten to one word in the title. I'm making progress. So the next natural question is, okay, this is the thing in real groups that plays the role of Soergel bimodules. You might be asking yourself, does this have a diagrammatic description? It's on its way. This is the PhD project of my PhD student, Victor Zhang. He's made some progress in specific examples. It turns out it's way more complicated than Soergel bimodules, but probably some type-specific diagrammatic world is possible. And then, oops, let me go back. So all I've done in this slide is I've just copied everything from the last slide and I've replaced B with K. But something I didn't mention about the last slide, which I should have mentioned, is that all the categories on the last slide that showed up were monoidal categories. So when I'm working in the world of sheaves, I have B equivariant sheaves on G mod B, so I can convolve them. That gives it a monoidal structure. The geometric Hecke category is also a monoidal category. That convolution descends to the geometric Hecke category, which is a non-trivial statement, but one can show it. And if we're looking at a category of bimodules where the same ring is acting on the left and the right, this naturally has a monoidal structure by tensoring over that ring. So the last slide, everything was monoidal, but here I've broken the symmetry. So now I have a different ring on the left and the right. I have a different group here to here. And so these things are no longer monoidal categories, but they naturally have a structure of module categories over the previous page. So this is the same diagram I just had with all the Ks. Now I have actions by the previous diagram. So the B equivariant derived category acts on the K equivariant derived category by convolution. This action descends to an action of the geometric Hecke category on both the category of semi-simple complexes and the piece generated by closed orbits. This is actually what I mean by the piece generated by closed orbits. I take the IC sheaves in here corresponding to local systems on closed orbits, and then I act by the geometric Hecke category, and I get something. And that's exactly the piece on which hypercohomology is fully faithful. And then downstairs, this category of bimodules has an action by RR bimodules by the tensor product. And that action descends to an action of Soergel bimodules on these Lusztig-Vogan categories. So the question is, this is the K version of the machine on the previous page. Does it work to study representations of real groups? So I have a question mark here because I've been, the machine works, it all exists, and one can define it. I have a question mark because I'm yet to actually prove anything unknown about real groups using this machine. So this is why there's a question mark, but I have hope that one could use this machine in that way. In particular, one could definitely use this machine to prove, there's a version of the Cauchy-Lusztig conjectures for real groups called the Cauchy-Lusztig-Vogan conjectures. They are some conjecture about multiplicities of irreducible admissible GK modules in principal series modules. And that theorem could certainly be proved using this machine if you wanted to, but it already has a proof geometrically, but this could provide an algebraic proof. But the thing that I'm more interested in at the moment, I'll get to in a second, is that like the previous story, everything downstairs makes sense for an arbitrary Coxeter group. And everything upstairs only makes sense for a Weil group. And so I'll tell you in a minute what these things look like for arbitrary Coxeter groups, but they're very mysterious categories, and I don't know anything about them. And so instead, at the moment, I'm kind of interested in that question, which is not really directly related to real groups, but is motivated by this picture. Okay, so what's the upshot of that? The upshot of that slide is that the geometry of admissible representations of real groups captured by K or G mod B, a piece of which can be reformulated algebraically as a module category over Soergel bimodules. Now I have a little asterisk here. For this talk, I'm trying to not talk too much about the theory of real groups, and so I'm not telling you what admissible means, but if you are a person who's interested in that theory, come ask me later, and I can tell you more. So a few features of this that I'd like to highlight. One is that this hypercohomology functor, it doesn't see non-trivial local systems, as I mentioned, which means that we only really get a piece of the geometry in this setting. The piece that we get is something called the trivial block. So this captures the bit of the representation theory that contains the trivial representation and lots of other representations, but it's not everything. And then, just as Soergel bimodules in the geometric Hecke category categorify the Hecke algebra, these Lusztig-Vogan categories, they also categorify something really natural, which is this module called the Lusztig-Vogan module over the Hecke category, over the Hecke algebra. And this module is the natural setting of Cauchy-Lusztig combinatorics for real groups. And so this is very beautiful. So there is a very beautiful Cauchy-Lusztig theory for real groups. It's well established and understood, and this is where it lives. And so what these are doing is they're categorifying this kind of Cauchy-Lusztig theory in the real group setting. Okay, I'm about to move on to telling you things that are a bit more precise. Any questions on motivation before I go? Okay. So, what actually is our category? So all I've done so far is I've given you a big geometric motivation with sort of big machines that I haven't defined for you, but this is meant to be why one might define these categories as I have. But the beautiful thing is that all that geometry is not at all necessary for their definition. So these categories can be defined with no mention to this geometry at all. The only input data we need is a Coxeter group and a reflection subgroup. I just point out for those of you who maybe like to think about Soergel bimodules, this reflection subgroup is not necessarily parabolic. So a Coxeter group is generated by some collection of simple reflections. And if we have a subgroup that's generated by some subset of those generators, we call that a parabolic subgroup. But there are reflections in a Coxeter group that are not the generators, and I'm allowing for those reflections to generate my subgroup as well. But once I have this information, a Coxeter group and a certain subgroup, oh, actually, I guess there's one last piece of input data. I need a natural representation of my Coxeter group, and I want it to be reflection faithful. If this is a Weil group, it's just faithful on the nose. Reflection faithful just means that a reflection fixes a codimension 1 hyperplane. But this information is enough for me to define my category. So how do I do it? Well, I can look at the cosets of this group under this subgroup. Because this is a reflection subgroup, some nice classical results in Coxeter theory by Dyer tell us that these cosets have a unique minimal length representative. If you haven't thought about Coxeter groups before, Coxeter groups have a natural length function. So they have a set of generators, and then they have a very simple set of relations in the group. And each element of the group can be defined in a minimal way, writing it in terms of generators. And that number of generators needed for a minimal expression is called the length of the element. And every coset has a unique element of minimal length. And so now I need to build a ring because I'm trying to build a category whose objects are bimodules over some ring. So what my ring is I take the symmetric algebra on this vector space. This is a polynomial ring. The number of variables is given by the dimension of this vector space. And I want to think about this as a graded ring because the gradings are very important in the story. Everything needs to be graded. So I'm going to grade this so that the variables are in degree 2, which is a weird choice, but it exactly comes from the fact that this is secretly an incarnation of cohomology. And so the cohomology of these varieties is generated by a degree 2 Chern class. So that's why this should be degree 2. Now, V is not just a vector space, it's a representation of this Coxeter group. And so this ring inherits an action of W. And my second ring showing up in my modules will be the invariance of this ring under this reflection subgroup. And I'll drop the W just for ease of notation. So RK is just this invariant ring. Okay. And now I need to tell you one definition of an object, and then I can tell you my category. So these are going to be the objects that generate the category, and I'll call them standard bimodules. So how I define them is I take my ring, R, some polynomial ring, and I want to consider it as a bimodule over itself. On the left, I ask that the structure is just the normal multiplication structure. We can take the ring as a module over itself by left multiplying. But on the right, I want the action to be twisted by a specified element of the bile group. So Rx is the standard bimodule corresponding to X, and the right action is just given by apply our element X to the polynomial and then right multiply. So these things are some class of RR bimodules I can define. Now I can restrict the left action to RK instead of R. And when I do that, some of these become isomorphic. So these standard bimodules are isomorphic exactly when X and Y are in the same WK coset. So what this means is that by applying this procedure, taking these standard bimodules for minimal coset representatives, I've come up with a collection of bimodules, and I have one for every coset in W mod WK. Now these guys generate my category. So here's how I can define the category. I take one of these standard ones corresponding to a minimal coset representative, and then I just tensor it with Soergel bimodules. I take every Soergel bimodule and tensor, and then I want to generate a category. So I want my category to be closed under direct summons. So if something is a summand, I want it to be my category in grading shifts. So this is I take this category and take its Cherebian envelope. So remember that, so what I'm doing here, these categories I'm defining are quite simple. They're additive categories. So they're not abelian categories. I'm coming up with some procedure to construct an additive category. And these are a category living inside of RKR graded bimodules. And this is a Lusztig-Vogan category. So this is how I can define it algebraically, just starting from a Coxeter group and a reflection subgroup. And I'll say a few words about how to think about this. Maybe these are more suited to people who think about Soergel bimodules already. So one thing to notice is that we always have the ring itself as one of our generators because the identity is always a minimal coset representative. And so if we just take R itself and act by Soergel bimodules, what we get is a copy of Soergel bimodules living inside the category, except that we're now restricting the left action to a subring. So that's nice. We have a copy of Soergel bimodules with a restricted action, which means that this kind of looks like singular Soergel bimodules, if that's a thing that you're familiar with, in the setting where a reflection subgroup is parabolic. If that doesn't mean anything to you, it doesn't matter. Another thing about this category is that these standard bimodules some of them are directly in the category because there are generators. And again, if you're a person who's thought about Soergel bimodules, you know that standard bimodules are not Soergel bimodules. So they're not usually in the category. And one of the techniques when you study Soergel bimodules is to do this procedure called localization, where you add the standard bimodules into the category in some formal way. But in our case, they're already in there. So our category looks kind of like a localized category, but only partially. So these are just kind of mantras for how to think about this thing. And then the theorem, I've got to have a theorem at some stage, is that if W is the Weyl group of a complex semisimple algebraic group, and if WK, embedded in W, is the Weyl group of RK, then this thing does indeed categorify the trivial block of the Lusztig-Vogan module. So that, my first slide was true. Okay, I feel like we've done an abrupt switch in content because now we're moving to like an algebra course. I'll pause. Are there any questions in the construction of these categories?
How can we define the trivial block?
Yeah, so the Lusztig-Vogan module is a module over the Hecke algebra, and it's not irreducible, and it's not even indecomposable. So it decomposes into a direct sum of pieces, and those pieces are blocks. And the trivial block is the piece containing the perimeter corresponding to the trivial representation. So the way that the Lusztig-Vogan module works is it has some it's just like the Hecke algebra. It has some natural basis, and the basis each basis element corresponds to an irreducible admissible representation of the group. And there is a natural action of the Hecke algebra. It has sort of a Cauchy-Lustig basis as well. And so if you look at the basis elements that are like, if you take the trivial representation and act, then you end up with a piece, and that piece is the trivial block. It's most of it. So like it's by far the biggest piece. So you capture a very large portion of it, but you don't capture everything.
Have we defined Lusztig-Vogan module?
No, and I'm not going to. Well, here's a cheap definition. It's the decategorification of this thing. So what I've defined is a category, an additive category, with an action of a monoidal category. And so if I take the split Grothendieck group, I end up with a module over the split Grothendieck group of that category, and that module is the Lusztig-Vogan module. Its definition is terrible. That's why I'm not defining it for you, but it's geometric. I mean, basically the way the definition goes is that you start with a generator for each of these orbits, and every orbit can have multiple local systems that are k-equivariant. So you take a k-equivariant local system on an orbit, and then you have a natural map. So you have a map from G mod B to G mod P alpha for some parabolic corresponding to a simple reflection. Then you have these push-pull functors that live in sort of categories of sheaves. So you can take one of these local systems, push and pull it under one of these maps, and that defines the action of the module for you. So that's the action of the generator of the Hecke algebra. So if you've seen kind of like geometric actions of Hecke categories before, they're often like this. So they're often you have some push-pull functor to some quotient by parabolic, and that's how this thing is defined in one way. It also has a crazy algebraic definition in terms of like certain types of Cartan subgroups within the real group. So you can write down a totally algebraic definition of this thing as well, but it's like case by case, and there's like 12 cases or something. So it's not very nice. Like it takes 2 slides to write down the definition. So I think that this definition is maybe the nicest one.
You said this is a module over the Hecke algebra.
Yeah. Yeah, Valentin?
You said that Cauchy-Lustig-Vogan conjecture was proved. Was it proved only for the trivial block or for everything?
It's proved for everything using D modules. So Valence and Bernstein localization works great for real groups, and it was actually Valence and Bernstein using the exact same proof as they used to prove the Cauchy-Lustig conjectures also proved the real group version. And that, like the Valence and Bernstein localization theorem, that theorem sees the whole thing. It doesn't just see the trivial block.
And do you understand how you could modify this to go outside the trivial block?
No, I would love to. I have some ideas, but they're a big change to the system. So this current strategy really only works for the trivial block. If I want to capture more, I would have to do something else. And so one thing is that there are multiple geometric descriptions of this Lusztig-Vogan module. One of them is what I've described, k orbits on G mod B. There's another one where you take 2 different real forms of the same complex group that are like Langland's dual to each other. And then you take the K corresponding to one and you take the K check corresponding to the other one. And then you take 2 copies of the flag variety and you act like on one copy with the K and the other copy by the K check. And then you look at pairs of orbits under this action. And these pairs of orbits also parameterize irreducible admissible representations, but there's no local systems. And so that's just like 2 pairs of orbits. It gives a parameterization. And so possibly like that version could somehow be meshed into this world and you remove the local system problem. But yeah, very far from actually knowing if that will work.
I have a silly question. So given G, is there a classification of the holomorphic involutions?
Yeah. Yeah, they're very nice. So there's the canonical source for this kind of stuff is Knapp. Knapp has written this big textbook called Lie groups Beyond an Introduction. And in there, he gives this classification. He does it in terms of Lie algebras, but you can do it that way. So you can classify real forms of a complex semisimple Lie algebra. And yeah, it's there. It's also the same classification of symmetric spaces, if you speak that world. So like instead of looking at K orbits on G mod B, you can look at B orbits on G mod K. And you can like classify symmetric spaces, and that is the same in a totally different kind of landscape. And people think about that in different ways as well. So that's another perspective in which one could look at this. Okay. So what have we built? So what we've just built is we've built for every pair, Coxeter group and reflection subgroup, a category. And our category is a module category over Soergel bimodules, and it's what's called Krull-Schmidt. So Krull-Schmidt just means that the endomorphism rings of indecomposable objects are local rings. But what that gives us is that if we have a Krull-Schmidt category, there are unique decompositions of our objects into finitely many indecomposable summons. So this property ends up being very important for how we think about these categories in the following way. So say we have such a category, a Krull-Schmidt category, where we have unique decompositions into indecomposables. How do we understand it? Like, what does it mean to understand a category? Well, if we have unique decompositions, every object decomposes into some list of indecomposables. So if we could classify all the indecomposables, and we know the action of the generators of Soergel bimodules on each indecomposable, then that totally tells us what the objects in the category look like. So that's the way we can understand objects in a category. But then it's a category, so it also has morphisms. So then we would also like to describe morphisms between indecomposable objects. So this stuff here is all growth into group information. So understanding the objects and how they decompose, this is all stuff that's the level of growth into groups. Then the real category information comes from the morphisms. Now, if our pair corresponds to a real group, then this categorical setting can all be decategorified. We can take the split growth into group and we end up with a module over the Hecke algebra. This is the Lusztig-Vogan module. And the indecomposable objects correspond to the Kaj-Lustig basis of this module. So this is a certain basis of the module that's dual under some natural duality operation. And this basis is what goes into the building of these polynomials. So the way the Kaj-Lustig theory works is you have 2 bases for your module, the standard and the Kaj-Lustig basis. You look at the change of basis matrix. That has a bunch of polynomials. That consists of polynomials. Those polynomials evaluated at 1 tell you information about representations. And so in our categorified version, indecomposables exactly capture the Kaj-Lustig basis, which is the hard basis. So that's nice. So in particular, we have one indecomposable object for every irreducible admissible representation in the trivial block. So we know how many indecomposables are in our category. We have a parameterization of them already from the fact that we know about the Lusztig-Vogan module. And we also know about the action. So the action of Soergel bimodules is exactly captured by the action of the generators of the Hecke algebra in the Lusztig-Vogan module. And this is captured in something called the W graph. So the W graph is some graph with a module that takes all of the generators and captures how the generators of the Hecke algebra act on that. So this first question here in understanding, if we have a real group, all of this information is exactly contained in the Lusztig-Vogan module. But this information is not. But also, if we don't have a real group, if we have some pair that doesn't correspond to a real group, we can still decategorify. We still get a module over the Hecke algebra. And I don't know anything about it. So there are indecomposable objects here. They tell us about a basis. So however many there are tell us the dimension of this module. But what the action is and what might possibly parameterize these basis elements is really mysterious. And so this is a bit of the story that I'm currently interested in because it's a very beautiful idea. So we have something here that has like a rough combinatorial description. This is an understood mathematical object, which is a bit complicated, but we have a description of it, and it exactly captures information about representation theory of real groups. This is defined in exactly the same way, and so it probably should behave in a similar way to this one. It should have some amount of structure, but what is it measuring? Unclear. And how is it parameterized? Unclear. Yeah,
So you have some positivity property above from this standard Kajdan, like let's say Kajdan Lusztig-Vogan polynomials. Do you have positivity below as well?
Great
What do you
question.
expect?
I expect it. Yeah, but I have no idea. Don't know how to prove it. So to prove positivity here, well, I guess there are multiple ways, but the obvious way is to build diagrammatics, because that was a consequence of Elias Williamson's proof in the first slide, is that they proved positivity for arbitrary Coxeter groups, and they used the diagrammatics to do that. And so if we were to try to kind of imitate that story in this setting, the natural thing to do would be to do this diagrammatically. So that's why we're working on diagrammatics. Yep.
What does positivity mean here?
Positivity means that the coefficients of these polynomials in the change of basis matrix are positive. So we have these two different bases of whatever module we get, and their change of basis matrix consists of polynomials. All of these categories are naturally, because these guys are graded, their Grothendieck groups have the structure of modules over Laurent polynomials with integer coefficients. And so the entries in these change of basis matrices should be Laurent polynomials. And then it turns out that they're all, they're not Laurent polynomials, they're on the nose polynomials, and all of their coefficients are positive. And so when you prove these statements geometrically for like a real or complex Lie group, those coefficients are described by like dimensions of stocks of sheaves or like ranks of D modules or something. And so they're just obviously positive because they're measuring a dimension of something. But then as soon as you get into this world where there's no geometry and they're not obviously measuring the dimension of something, it's not obvious that they're positive. And then that's a big question.
You have one basis coming from indecomposable.
Yes.
What's the other basis?
So the other basis is so that's a good question. In this case, I'm not really sure. In this case, the other basis is built into the theory. And so here you define this thing using a different basis, and then you prove the existence of this self-dual basis. And so, yeah, I don't actually know. I assume there's another basis here. I assume I could imitate it. Well, yeah, I'm not even sure. I'm not sure how to define it.
But you said you expect positivity.
Well, because I expect that one could define it. So the thing that's tricky is that there's not actually an object in either of these categories whose class in the Grothendieck group gives the standard basis. So this is like a feature of this story, that indecomposables give the Cauchy-Lustig basis, but there's not something that gives the standard basis. If you move this up and work in the homotopy category instead, then you can take like complexes of things and then you get something that gives you the standard basis, but it's a little bit subtle. And so presumably you could do the same thing here. And that's probably how one could do this. But I haven't thought about it at all, so I haven't tried. But I expect, the reason why I expect it is because this is like exactly how the story goes for Soergel bimodules, just with this extra information of a subgroup. And so, yeah, that's why I expect it to be true. So maybe hope is a better word than expect. I don't have any evidence. Valentin?
I just want to clarify something. So in when you say the Cauchy-Lustig matrix corresponds to the composables, that's in this category of Soergel bimodules, or
that also holds for Soergel bimodules. So I'm talking about indecomposables in this category.
but when you go to the real group, will you have something like a standard and irreducible module and some correspondence between standard and Cauchy-Lustig basis?
Oh, no, so this is a statement about real groups. So here, this indecomposable is in the Lusztig-Vogan category. It's not in Soergel bimodules. And this corresponds to the Cauchy-Lustig basis of the Lusztig-Vogan module.
So should I think of M as a real group module or a GK module?
No.
No.
That's a bit of it, but it's the same with Soergel bimodules. It's a temptation. But the tricky thing is that all of these things are really like extracting away the interesting information about the categories of representations. So if you're probably more used to the story where you start with categorial, move to D modules, move to perverse sheaves, and each of those things are like an equivalence of abelian categories. And so you can really think about a perverse sheaf as corresponding to a specific representation. And you have like the standard and the irreducible ones, and those correspond to the standard and principal series or something. That's not what's happening here. So in this world, when we were in the equivariant derived category and we took the semisimple complexes, we stripped away all of that type of information. And so really this is just kind of counting parameters. And then like the magical realization of Soergel is that you didn't need it. And so what Soergel realized is he was just trying to solve the Cauchy-Lusztig conjectures. And he didn't actually need a whole category that had objects corresponding to the representations. He just needed something that captured enough of like the combinatorial information of the Hecke category to capture this change of basis matrix. And that's what's going on here. But you lose those nice associations. So I don't have like a representation corresponding to this. Yeah. Okay, cool. So this is what I'm interested in. That's why this has question marks. What do these guys look like? I don't know. I can't tell you anything yet either because I don't know the answer, but that's what I'm thinking about in the future. But what I will do, oh, I am going long, huh? This is so nice. Thank you for asking me questions. It's so much nicer to give a talk when people ask questions. So what I want to do at the end of the talk was do a few examples, just so these things are a little bit more concrete. And so I'll do these. Maybe I'll go a little bit faster through this and then we can end.
Still have half an hour.
I know, but yeah, 90 minutes is a long time. When we have 90-minute seminars, we take breaks in the middle.
Okay.
But you guys have the endurance.
We are
so
hardcore people.
You're hardcore. I can keep going. Okay, so let's do some. So the reason why I want to do examples is because these are really nice. This is a very fun world to work in. They're like things you can just do by hand because these are categories. These objects are modules over polynomial rings. So you can write down what a module over a polynomial ring looks like. You can take the tensor product of two modules and it turns into like exercise in an algebra course. And so I'll show you some of the first few examples. And the other reason why I want to do this is because I started doing the easy examples by hand in order to try to find techniques that are going to work in general. Because the structure of the sort of the useful thing about this world is that it strips away everything about the real group. And so these are just examples with polynomials, and anything that works for a Weil group really should also work in general as well. And so I'll show you some techniques along the way that are not specific to real groups that work for any setting. Okay, so let's start with the easiest one, a type A1 example. This is the category capturing the representation theory of SL2R. So this is actually the example you asked about earlier. So in this case, our input data is a Weil group and a subgroup. Here, the Weil group was meant to be the Weil group of SL2C, which is Z mod 2Z. WK is the Weil group of SO2C, which is trivial. So that's our situation. So if we look at the cosets, our cosets are just given by Z mod 2Z. And the invariant ring is the ring itself. So this is the one example where we have the same ring acting on the left and the right. Every other example, the rings change. And this information here tells us that our category has two generators because the generators are given by these quotients. So here's our category. It has two generators and we act by Soergel bimodules, and it's living in a category of graded RR bimodules. Also, I should say the R is here. It's just a polynomial ring and one variable. Okay, so here's our category. And I kind of told you previously what I want to do to understand a category. The first thing I want to do is find indecomposables. So if we have a description of a category where we know the generators, we understand the category that's acting, what's the most naive way we could find indecomposables? Well, we can start with the generators. Those are probably indecomposable. They are. And then we can act by generators of the category. So Soergel bimodules of type A1 have two indecomposables in that category. There's just the ring itself, and then there's this guy, which is a Bott-Samuelson bimodule, which is the tensor product of R with itself over the invariance by the only non-trivial element of the Weil group. And then there's a shift for various reasons. So this is an element BS. This is an element of Soergel bimodules. It itself is indecomposable in the category of Soergel bimodules. So if I want to find indecomposables, I can start with my generators, act by indecomposable Soergel bimodules. Notice I only need to act by indecomposables because if I act by something else and it decomposes, then that information all filters through. So it's enough to just act by the indecomposables or go by modules. And then I need to decompose. So I need to see what I get, decompose, and then I need to check that all the summands that I get are actually unique and see if there's any isomorphisms between them. And then I just need to keep going. I need to take the things that I got, act by the generators again, repeat the process. Take the things that I got, act by the generators again, repeat the process. So this is not slick. This is just the first thing you would do if you were trying to do this by hand. And for an example like this one, it works. So let's do it. So we have two generators, R and RS. And I want to act on each of these by the two indecomposables or go by modules. Action means tensor product over R. So if I take R, tensor over R, this one's easy. That's just R. If I take R, tensor over R with BS, oh, sorry, that one's indecomposable. Check. R tensor over R with BS, that is R BS. This is also indecomposable. We have a few checks. Maybe this is a little bit less obvious that this is indecomposable as an R-R bimodule. One useful thing we can do in this world is because our ring R is positively graded, it's a polynomial ring. If we have such a ring acting, bimodules over that ring, if they're generated by a single homogeneous element, meaning that it lives entirely in one degree in the graded piece, then they have to be indecomposable. And so this one is generated by one tensor one. Remember that BS is R tensor over RS R. So we can get everything just by acting on one tensor one. And so this is indecomposable. Okay, so we found two of them already. That's pretty good. RS, if we tensor with R over R, again, this isn't doing anything. And so we end up with RS. That's indecomposable as well. Now, this is the only interesting one. So if we take this interesting standard bimodule, tensor over BS, we end up with something that looks like this. This is something unfamiliar. Is this indecomposable or does it decompose? Well, the first thing we can notice is that if I write out what BS is, it was the tensor product of R with itself over RS. And so there's some R's tensoring with R in the middle that cancel out. So this just looks like a tensor product of R with RS over the invariance. And now we have to get really into the weeds of how these things are defined. So if you remember how I defined RS, it had a right action of R, but it was twisted by the element S. So if I'm taking the tensor product on the right with the invariance, if something is invariant by S, when I twist it by S, it doesn't do anything. And so that means that this is isomorphic to just R instead of RS, because the only things that I'm acting on the right are invariant already. Now this is BS. So this thing that seemed like it was interesting was actually isomorphic to something we knew. Cool, that's already on our list. It's indecomposable, but it's already on our list. Okay, so what do? So this is the first layer. We started with the generators, we acted, we found an isomorphism, now we repeat. We know what's going to happen with R and RS because we already did that one. So we don't have to do those are done. But the only thing interesting is what happens if we take BS and we act again. So we know what happens if we act by R. Acting by R doesn't do anything. So the only interesting thing that could happen is if we take BS and act by BS. So that's the tensor product of BS with itself. Okay, now what does this look like? Well, if we write it out, this looks like 3 copies of R tensored with itself. Both the times the tensor product is taken over the invariance, and then there's some shift going on. And now we play some nice slick games. So R is a polynomial ring in one variable. Something we learn about polynomials when we're in, I don't know, elementary school, is that polynomials are either, we can write any polynomial as a sum of an even polynomial and an odd polynomial. You can take all the even bits and all the odd bits, and that gives us a decomposition of this ring into the direct sum of the S invariants. The even ones are all going to be invariant by S, and the odd ones shifted by -2. So we can do some slick decomposition of R into this. This decomposition only holds on the level of RS bimodules, but that's fine because this copy of R is sandwiched between 2 RS's. Then we can do some decomposing. If we split up this direct sum, what we get are exactly R tensor over RS with another copy of R. And we have 2 of them, each with a shift. So we end up with 2 copies of RS back with itself. And that means we don't get anything new. So when we tensored BS, we took a tensor product, it ended up being a sum, which is a kind of strange situation. But in particular, there's nothing new. And then if we keep doing this, nothing else is going to show up because we're just going to get more and more copies of BS. Okay, so what's the conclusion? The conclusion is that our category has 3 indecomposables, and the action looks like this. So we take our generators. If we act by BS, we get BS. And then if we continue acting by BS, we just get BS forever. That's nice. Just a comment for those who might be familiar with the geometry of real groups, what representations these correspond to. So if you look at the k orbits on G mod B in this example, G mod B is a P1, CP1, which I like to think about as a sphere. K is SO2, so it's going to be like a circle reflection or rotation action. So there are 3 orbits, the North Pole, the South Pole, and then the copy of C star that's in the middle. And these 2 correspond to the local systems, which are just on the North and South Pole, this closed orbits. This corresponds to the trivial local system on the open orbit. And there's one other interesting local system that our category doesn't see, which corresponds to some, like the second principal series representation of SL2R. Okay, that was probably incomprehensible, sorry. So this is like an exercise that I would give to my algebra students, and it's quite fun. And so when you do this first one, you think, okay, like maybe I can do this. Maybe I can do these things by hand. So let's try to extract what we got from this to see what we can do to do this in general. So if I want to take my same recipe, which is my naive recipe, what do I need if I want to implement this in general? Well, I start with the generators. That's easy. I just am given the generators. I act by indecomposables or go bimodules. That's easy just because I know what all the indecomposables or go bimodules are already. There's like a nice theory there. There's one for every Weyl group element, by the way. This one's hard. The decomposition and the finding isomorphisms. So how do I do this? What I need some tools for decomposing. I need some tools for showing that 2 modules are isomorphic or not. And I need some tools for showing that something is indecomposable. And that ends up being quite a hard one. So what do I have? Tools for decomposing. Well, how do you decompose a module? One way to do it is to put it in the middle of an exact sequence and show that that short exact sequence splits. And so what's the data of a sequence? Maps. So to decompose something, you really need morphisms in your category. And those morphisms could be built using diagrammatics. But then there's another really cool tool, which is that this thing is a module category. And it's a module category over something we really understand. Like we know Soergel bimodules, we know how they multiply. And it turns out that sometimes we can really use this. So we can kind of play these games where we know what Soergel bimodules looks like. And the knowledge of the monoidal category that's acting can sometimes be enough to tell us information about our category in a really lovely way. So this is kind of a slick tool, and this is a brute force tool. Now, isomorphisms, again, how do you establish isomorphisms? You need a morphism. Or you can show the 2 things aren't isomorphic by showing they have different standard factors and some sort of filtration. Now, in decomposability, again, we can kind of get this if we're clever with our knowledge of Soergel bimodules. And we can also just do it in a brute force way by remembering that we're just working with modules over polynomial rings. People have studied these a lot. There are a lot of theorems about modules over polynomial rings. Sometimes those can help us. Okay, so that's step 3. Step 4, we have to repeat this. So how do we keep repeating this? Like in the case where we have a real group, we at least know that this terminates, but do we even know it terminates in general? So we either need a lot of patience or we just need something stronger. And so it turns out that we can take this recipe, which seems kind of naive, but this is exactly the kind of thing that's useful if you want to plug it into a computer, and we can implement it. And that's really the way to do this. So the goal with all of these are to develop tools that work for arbitrary Coxeter groups. I should say that I wrote down all the tools that currently exist. So this is in joint work with 2 of my students, Victor Shung and Daniel Dunmore. Okay, I'll show you one more example where the tools come out, but we won't do any more details. So this is fun. We always do type A examples. Let's do a type C example. So this corresponds to a real symplectic group, SP11, which is some collection of matrices that preserve both a Hermitian form and a symplectic form. But we don't care about that. All we need is the Coxeter group and its subgroup. So here's the Coxeter group. It's generated by 2 reflections, and they have the relation that st to the 4th is 1. So this is some braid relation that says st is equal to tsts. Here's the type C2 root system. Now my subgroup that I take ends up being one that's generated by S, the generator, but also TST. So TST is a reflection that's not simple. So it's one of these examples of a reflection subgroup that's not parabolic. TST happens to be reflection across this axis. So it sends this root vector to this one, and then S sends this one to this one. Okay, so if I take the cosets, this is a group that has 8 elements, and I'm taking a quotient by a group of size 4, and so I should end up with 2 cosets. Sure enough, I do, WK, and the other minimal coset representative is T. Here's a picture of the Bruhat graph of this group, and here are my cosets. So it's kind of disconnected in this interesting way. Okay, what's my ring? My ring is now a polynomial ring in 2 variables. I'm going to choose those 2 variables to be the ones that correspond to perpendicular vectors because that makes my life easier. And then if I look at my invariant ring, it turns out that it's just polynomials in x squared and y squared. Okay, now I have my category generated by 2 generators. I act by Soergel bimodules of type C2 and see what I get. Okay, so we'll play the same game as before, but I'll do it a bit faster. 2 generators. I have 2 interesting Soergel bimodules to act by, BS and BT. Now, when I do this, the first layer returns 4 objects. Are these indecomposable? The first one isn't. One can develop a lemma, which is really just like writing down maps of polynomials. This one didn't require diagrammatics. We just wrote down a map. And we can show that this thing splits. So that's not indecomposable. This one is indecomposable. We can show it by playing games with the monoidal structure of Soergel bimodules and using the fact, the Kroll-Schmidtness, that we have unique decompositions. This one splits again by a similar splitting lemma to that one. This one is secretly something else that's already on the list. One can show that anytime we have this situation where this T is the same as that T, then we have an isomorphism here. This is the same isomorphism that we saw in the previous example. So our first level gets us nothing new, a new indecomposable, nothing new, something that we're already isomorphic. So we only got one new thing. And then we repeat. So all we need to do is look at this one. We act by BS and BT. What do we get? We have something of length 2, something of length 2. Things are getting harder, but luckily this one splits. We can see this just using Soergel bimodules. This is the same computation as I did on the previous slide. Now this one is more interesting. So this one splits into our 2 generators plus something new. We can get this decomposition by knowing just stuff about the Soergel bimodule structure, but we don't know anything about the new thing. So that's our last step. There's a new indecomposable. Well, actually, we can show it's indecomposable. So there's a new indecomposable, but what does it look like? So we keep going. The last step is we can show that this indecomposable is something we recognize, and we can write down specifically its structure. Now, this is tricky. The reason why we know this is through diagrammatics, and the maps in this situation are crazy. Like, we've written them down in the terms of polynomials, but it's some enormously complicated map on polynomials that you could never come up with unless you knew the diagrammatics. So in this example, we guessed the diagrammatics just by knowing what the picture should look like. This gave us a correct map that worked. And the final step is that if we take this guy and act by BS or BT, we get the same thing back. So the algorithm stops. So what's the picture? Here's this category. Again, it's not too bad. We have 2 generators, and now we have 4 indecomposables, and our action kind of moves around in this way. So what are our observations? The first is that things that are indecomposable as Soergel bimodules can decompose in our category, which makes sense because we're changing the ring on the left that acts. Then the other thing we can notice is as soon as we get past the first layer, we really needed diagrammatics. We were kind of stuck without it. And the last thing we can notice is that we could go pretty far just using information about the monoidal structure of Soergel bimodules. Now, the reason why I'm emphasizing this, I think I say on the next slide, is that this is really, if you trace back what this is doing, this is using information about representations of complex semisimple Lie algebras to tell us information about real groups. And that's interesting. So that's something new. If we can figure out how to really lean into the structure of Soergel bimodules here, then we can use known information to extract stuff about a strictly harder situation.
So here, those numbers in parentheses is the grading.
Yeah.
Then the grading in the end doesn't play any role.
It plays an enormously important role. Yeah. So everything really needs to be graded. And the reason is because that grading descends to a structure of like a algebra over Laurent polynomials. So the Hecke algebra has coefficients and Laurent polynomials. Those polynomials capture the grading, but those polynomials are what give us like polynomials and Cauchy-Lusztig polynomials. So we have to keep track of this grading to keep track of the polynomial information downstairs, which is actually the information we care about. Like that's the stuff that captures information about the groups.
So in the conclusion picture, so
Oh, why aren't any of these things graded? Is that what you mean?
yeah.
Yeah, it's because the grading is built in. So BT, its definition has a shift of 1. And this is actually wrong, I should say. Actually, that's a good point. This should have a shift of 2 in this definition. So I define the indecomposable to have a certain shift, and that shift has to do with a certain duality. So I have, in these categories, I have infinitely many indecomposables because every time I take one and shift it, I get a new indecomposable. So what I want is to pick out a specified most important indecomposable that has a certain shift. And there's a recipe for what that shift should be. And it has to do, it's a relationship with W and WK. And those shifts, like it's important to make the right choice.
So that in the conclusion picture, grading is kind of hidden.
Yes.
But it's very important.
But it's hidden, but it's important. And this was sort of has to do with Valentin's question earlier. He was asking if we have a recipe to take one of the objects in this category and return a representation. And I said that Soergel's idea was that we don't need that. We don't need to have these equivalences of abelian categories, but the grading is what makes up for it. So the grading in Soergel's story, the fact that everything is graded is really important. And that grading is exactly what allows you to move to the additive structure and forget about the abelian structure in your original categories. So it does play a really important role. Yeah. Okay. Just for fun, I'm just going to show you a harder example. So these are basically the only examples we can do by hand. And so as soon as we get harder, like the next biggest example is G2. And this is already impossible. So here's our vowel groups. They're not that different. The only difference here is this is a 6 instead of a 4. But this is the category. So the category jumps up to having many more objects. And we tried, but we could only get this far using our techniques. And then quickly we got stuck. But we can take all our techniques and just implement these in any computing software that knows something about polynomial rings. And so we did it in Magma. And then this spits out the W graph. But the problem is that our algorithm makes an assumption, which we only know to be true for a real group. So we're only sure that our algorithm spits out the correct answer if we're working with a real group. Otherwise, our algorithm spits out an answer, but we're not quite sure if it's correct. Probably is. So from here on, we use computation. Okay, so I'll finish up. Here's my takeaways. So what have I done? This whole process produced a zoo of examples of module categories over Soergel bimodules, which is interesting. I'm not the only one who's thought about these. Lots of people study module categories over Soergel bimodules. And in fact, there are some papers that classify all simple module categories over Soergel bimodules. So an interesting question is how these categories relate to those. Because when one can study, sort of classify certain module categories over a given monoidal category, it's quite abstract. And so this is like a really natural example of a module category that showed up in nature. So it's interesting to know how it relates to these classifications. So that's cool. It's clear from this that we need diagrammatics. So yeah, it's not just useful, it's essential. So we got to encourage Victor. And this is what I mentioned 2 slides ago. We can get a lot of leverage if we know stuff about Soergel bimodules. And this is really interesting because this means that we're gaining information about admissible representations of real groups from categorial. And this is where I hope to actually prove something kind of new. So if we could have a relationship like this would allow us to possibly prove things about Lusztig-Vogan polynomials using just information about Lusztig polynomials. And Lusztig polynomials are hard, like anyone who's worked with them knows that they're hard, but they just require a vowel group. And so in some sense, they're simpler, whereas Lusztig-Vogan polynomials require all this crazy geometry. And so they're way more involved to define. So that's an avenue that I like, but I'm totally unclear how much we get this way. And then finally, this was sort of apparent from my initial picture, this sort of looks like a hidden geometry situation. We can define these categories that look like they should be cohomology of something. Remember in my initial picture, our categories appeared as cohomology of some geometric object. these things are going to behave a bit like their cohomology, but there's no geometry. And that's cool. So can we say anything about that? I don't know. And that's all I have. Thank you. There are questions?